All right, welcome. Today we are going on a journey, a trip from the total wild west of data management. I'm talking chaos and inconsistency to the beautifully structured and ordered systems that, well, basically run our entire modern world. Let's dig in and see how it all works. So here's the game plan. We're going to start with the problems of the past, then get into the core ideas of schemas and states. After that, we'll see how different levels of abstraction help team all that complexity, which leads us to this really elegant solution called the three-schema architecture, and its ultimate superpower, data independence. I mean, really think about that for a second. You've got countless people pulling money out, putting it in, sending it around the globe. How in the world does it all stay perfectly spot-on accurate? Well, it's not magic, that's for sure. It is the result of some incredibly clever database design, and that's exactly what we're going to break down right now. To really appreciate just how brilliant modern databases are, you have to understand the absolute mess they replaced. See, back in the day, applications were built right on top of basic file systems, and let me tell you, it was a recipe for disaster. This list right here, this is basically a developer's worst nightmare. You had the same data copied all over the place, which of course led to all sorts of inconsistencies. If you wanted a new report, well, time to write a whole new program. Data was trapped in separate files and weird formats. And the basic rules, simple things like an account balance has to be above 0, those were buried deep inside the program's code, making them a total pain to manage. And this quote, this gets to the absolute heart of the problem, what we call atomicity failures. So imagine you're transferring $100. The money gets taken out of your account, but before it lands in the other one, the system crashes. With those old file systems, that money could just, poof, vanish. A transaction has to be all or nothing, and these systems just couldn't guarantee that. And this really shows you the huge shift in thinking. The old way, it tangled all the data logic up inside each program, which is what created that mess. But the modern database approach, it's totally different. It builds a central fortress for the data. The database actually knows its own structure, it's self-describing, and it creates this clean separation, this insulation between the data itself and all the programs that need to use it. Okay, so how do we build this data fortress? Well, to get that clean separation, we need a way to describe the data's structure, kind of like how an architect creates a blueprint for a building. And this brings us to two really fundamental concepts, the schema and the state. The database schema, that's the blueprint. It defines exactly what the data looks like. For example, it'll say that a student record has to have a name, an ID number, and a major. You design it super carefully, and it's not supposed to change often, just like the actual blueprint for a skyscraper. Now, the database state, that's the building itself, but it's alive with activity. It's all the actual student records, the real names and ID numbers frozen at one specific moment in time. We sometimes call this a snapshot, and unlike the blueprint, this thing changes constantly, every single time a new student registers or somebody switches their major. So here's a super simple way to think about it. You've got the schema, that's the blueprint, the intention, and it rarely changes. And then you've got the state, that's the living, breathing building, the extension, which is changing all the time. The whole job of the database is to make absolutely sure that the building always follows the rules of the blueprint. All right, we have our blueprint. But modern databases are, let's be honest, incredibly complex. So to manage all that, the system uses a really clever trick called abstraction. It's basically a way of only showing you the details you need to see, depending on who you are. Yeah, data abstraction is all about hiding the messy bits. I mean, you don't need to know how the data is physically laid out on some spinning magnetic disk just to check your bank balance, right? The system shows you only the essential features, giving you a much simpler, cleaner view of things. And this abstraction happens on different levels. Way up at the top, you've got the high-level or conceptual model. This is how we humans think about data, as employees who have names and work on projects. Then in the middle, the representational model organizes all that into structures, like tables. And way down at the bottom, the low-level model gets into the real nitty-gritty of how it's all physically stored on a disk. This brings us to the master plan that ties this whole thing together. It's called the three-schema architecture, and it is the brilliant solution that organizes these different levels of abstraction to perfectly separate what the user sees from how the data is actually stored. So this whole architecture works in 3 layers. Up top, you have the external level. This gives a custom view for each user. An accountant sees financial data, a school registrar sees student grades. You only see what you need to see. In the middle is the conceptual level. This is the master blueprint for everybody, defining all the data in the system logically. And then at the bottom, the internal level describes how all that data is physically laid out and stored. The thing that makes this all work is the database management system, the DBMS. It acts like the super sophisticated translator. So when a user makes a request from their custom view, the DBMS maps that request down to the master blueprint, and then maps it again down to the physical storage to go get the data. It's totally seamless. And now for the grand finale. Why go through all this trouble? Creating separate levels, all this mapping? The answer is one of the most powerful ideas in all of computer science: independence. Data independence is, in one word, freedom. It's the freedom to make changes to one part of the system without breaking everything else. It means our blueprint can evolve over time without forcing a total teardown and rebuild of every single application that relies on it. This architecture gives us two incredibly powerful kinds of freedom. First, you've got logical data independence. This means you can change the master plan, like adding a birth date to a student's record, without totally wrecking the accountant's financial reports. Then, you have physical data independence. This lets you change how the data is actually stored, say adding an index to make searches way faster, without changing the master plan at all. It's amazing. So when you boil it all down, all of this clever design, the schemas, the levels, the mappings, it all serves one single beautiful goal: freedom. The freedom to evolve our data systems over time without causing total chaos for the thousands of apps that depend on them. This structure is what brought order from chaos, and it's what enabled the data-driven world we all live in today. But as data becomes more and more valuable, more complex, from AI models to massive global networks, the big question remains: what's next for the blueprint? How will this genius design have to evolve to keep up? Thanks for joining me.